Hello and welcome to lesson number 16, differentiation. So, differentiation is a very important topic, not only in mathematics but also in real life. You use it all the time. You might not be aware that you're using it, but you do use it all the time. Differentiation is the study of the rate of change of one value when you change a different value, or at a certain point along the relationship of two different values. When you change one value, how much does the other value change by? So what I mean by this is, given a relationship like what I've drawn here in this graph, where we have f of x on the vertical axis and x on the horizontal axis, when we change x by a certain small amount, what happens to y? So let's say over here, what happens to y as in f of x when I change x by this amount? What is the rate of change of y at this point here? So in this case, it might not be too clear how exactly we are supposed to solve this. However, when we have a straight line, it's very easy to solve this question. So what we want to find in this thing, in derivation, is how fast one value is changing while another value changes. So on a straight line, let's say we have 2 points. Let's say this point here and this point here. Let's call this point as x1, y1 and x2, y2. So here between these 2 points, there is a change in x coordinate and a change in y coordinate. The x coordinate change is this change here, which I'm going to represent by delta x. Remember, delta indicates the change of. So here we have the change of x. This is not two values. This is not delta times x. The whole symbol delta x is one symbol representing the change of x. When we do this change of x, delta x, here you can see there is a corresponding change of y, which I'm also going to label delta y. Again, delta y is one symbol, not two symbols. Delta y in itself is representing the rate of change of y. So here you can see from these coordinates, delta x is going to be the difference of x2 minus x1, so x2 minus x1. And similarly, the change of y here is going to be y2 minus y1. So this is y2 minus y1. So now, what is the relative change of y relative to x? Well, considering what we just said, the rate of change of y relative to x would be delta y divided by delta x, because for each change in x, what we are asking is how much does y change. For a particular delta x change, y changes by delta y. So for any change per delta x change, we need to have that delta y change. So therefore, the rate of change here, which I'm going to say as rate of change here, is delta y divided by delta x. And you can see, since this is a straight line, no matter where you look, you have the same exact value. Over here, over here, over here. The ratio of this side to this side is always constant. The reason for this is, of course, when you have a straight line, this angle theta is always constant. Because this angle theta is constant, tan theta, or the ratio of this thing to this side length, is always going to be constant. Therefore, the rate of change, which in this case you can see is exactly the same thing as what we mean by the gradient, is also constant. So, for a straight line at least, what we are looking for, the rate of change is also the gradient. So here I can even write gradient is equal to the rate of change, which is equal to delta y divided by delta x, which is equal to y2 minus y1 divided by x2 minus x1. So for a straight line at least, we can find the exact rate of change of this straight line, as in the gradient of this straight line, using 2 points on the straight line. So here this straight line is in the form of y equals mx plus c. The quantity we are looking for is the value m, and we can find m simply by using any 2 points that we know are on the line. However, this simple easy method does not work for a curve. We can see here on this curve, if we want to find the rate of change here, i.e. we want to find the gradient at this particular point, i.e. we want to find the gradient of the tangent line of this curve at this point, we cannot easily do it. You can see here, we only have a single point, let's say x0, f of x0, because here we don't have the y-axis, we instead have the f of x-axis. So here, this coordinate here is x0, f of x0. We do not have an easy method to find the gradient of this line here. However, consider this. we can find any other point on this line, this curve over here. And we can draw a straight line between these two. Now you can see here clearly, when I draw this straight line is not identical to the tangent line we have drawn. But the gradients of these two look kind of similar, don't they? I mean, it's not exact. You can see if I extend this line outward, these two definitely have different gradients. But the gradients are kind of similar. Now observe what happens if instead of this faraway point here, I pick a closer point to the point we're interested in. Let's say this point here. If I choose this point here and then I draw this line which is connecting the point of interest and the other point, hold on, not this, like this, you can see now the gradient of this line that we just drew is much closer to the gradient that we're interested in, the gradient of the tangent. If I bring this point even closer, then doing the same process, that line would have a closer gradient to the line we are interested in. In fact, as we bring this point here arbitrarily close to the point of interest, then the gradient of that line that we're constructing by connecting this point of interest and the other point we constructed is going to get arbitrarily close to the actual point, actual gradient we're interested in, which is the gradient of the tangent. So then we have a process. We have a process that we've just figured out, that if we take some point that is on this line and we bring that point very close to the point we're interested in, then the gradient of this line is going to get very close to the gradient of the tangent line at that point, i.e. the rate of change that we're interested in. We have a concept for this. If you don't remember that concept, go back to this video here. This concept is the concept of limits. What we are interested in here, rephrased, is what happens as to the limit as this point gets arbitrarily close to this point. So we're interested in the limit as this point approaches this point of the gradient of this line here. Before we continue, I should mention some certain terminology. This line here is a tangent line because it is touching this point locally at this curve locally at only this point, and this other line here that we've been drawing is something called a secant line. Secant line. This line is a line drawn between 2 points along a curve. So you can see the secant line is this line here, the tangent line is this line here. If we rephrase our statement earlier, what we're interested in is the limit of the gradient of the secant line as this second point approaches the first point here. So now let's draw some things. Like here we've only been talking about this in terms of arbitrary values. Let's now draw some real numbers, as in symbols, and try to evaluate what we're actually looking for here. So considering a graph like this, if we consider a graph of f of x versus x, and we draw a curve like what we had earlier, and we consider certain values, let's say this curve is like this, this function is f of x and we have x here on the x-axis. Let's say we're interested in this point here, and this point here we're going to call x sub 0, comma f of x sub 0. This is the point we're interested in. Let's say this other point is a certain distance which I'm going to call dx away. Now here dx is not some symbol d times some symbol x, it is its own quantity dx. It's similar to the delta x we had earlier, except in differentiation I'm going to put a different symbol, dx. Some places use the symbol h to represent this quantity. Some people just say delta x. I'm going to put dx because that's the way that I learned it and that's the way I like it. So here, this second coordinate here of this point here that we're considering is a distance dx away in the positive x direction. If this first coordinate is x0, the second x coordinate here is going to be x0 plus our dx. Similarly, if the x coordinate of this point here is x0 plus dx, then the y coordinate corresponding should be f of that value. So this y coordinate here is f of x0 plus dx. Similarly, of course, this original coordinate that we had here is f of x0. So we have this. Now, considering this, I'm going to call this change in height here dy. It is the change of the y-axis, in this case f of x, actually we'll call it d of f of x. This symbol here is representative of the change, the small change of f of x that resulted from the small change of the x-axis dx. So here, if we draw this line here, the gradient of this line which I've drawn here is the second y coordinate minus the first y coordinate divided by the second x coordinate minus the first x coordinate. So therefore, drawing that over here, the gradient we're interested in is the change of the y coordinate, which is f of x plus x0 plus delta x dx, minus the initial y coordinate, which was f of x0. So we have f of x0 divided by the change of x. So here x2 is x0 plus delta x and x1 is x0. So we have x0 plus dx minus x0. You can see here a kind of symmetry. On top we have f of x0 plus dx, and on the bottom we have x0 plus dx. Over here we have x0 and down here we have x0. So we have a kind of symmetry here. We can actually simplify the denominator here. We can see here there's an x0 and a minus x0. Cutting the two, we can see that the gradient of the secant line that we're considering here is f of x0 plus dx minus f of x0 divided by dx. Now then, as we described above, the gradient of this secant line is going to get closer and closer to the gradient of the tangent line as the horizontal distance gets lower, i.e. as this point here gets closer and closer to the point of interest over here. So then, considering that, in this graph here, what we want to do is reduce the distance dx, because if we reduce the distance dx, then this point is going to get closer and closer to the actual point we're interested in, x0, f of x0. So then what we have to do is reduce dx. We have an operator for this. When we want to reduce this thing gradually without turning it into 0, what we want to do is to take the limit. So therefore, the gradient of the tangent, is equal to the limit as dx approaches 0 of this quantity here. So what we want is the limit as dx approaches 0 of the quantity f of x0 plus dx minus f of x0 divided by dx. I apologize, I've only put d there, it's supposed to be dx. This is what we're interested in. The gradient of the tangent at the point x0, f of x0 is the limit as dx approaches 0 of f of x plus dx minus f of x0 divided by dx. This right here is what we call the first principle definition of the gradient, or the first principle definition of the derivative. The derivative of a function at a particular point x0 is going to be this right here. This has different notations. Some people in some places denote this as dy by dx, as in the change of y by the change of x. This is equal to the limit as dx approaches 0 of f of x0 plus dx minus f of x0 divided by dx. This is the dy by dx at the point where x equals x0. So we could say at x equals x0, dy by dx is equal to this quantity. Some other people take a different approach to representation. They say this thing right here could be written as its own function. So we have a different function, and that function gives us the gradient of this other function f of x at a certain point, and we denote that function as f prime of x. So we say f prime of x is a function that gives us the gradient of this graph f of x at a certain point x. So therefore this is going to be equal to the limit as dx approaches 0 of f of x plus dx minus f of x divided by dx. This is a different approach to representing the same exact thing. Over here on top we are saying at a specific value of x, dy by dx is this. Over here we are instead saying there's some function f dash of x which gives us a certain the rate of change of the certain function f of x at that particular point. So here, this is one way to represent it, this is another way to represent it, there is yet another way to represent it, which is this, y and then a dot. The dot indicates the rate of change of the value y with respect to an assumed value, which in this case is x. So in this case, this would also be representing the same exact quantity of the limit as dx approaches 0 of f of x plus dx minus f of x divided by dx at a particular point, which in this case we're going to consider as the point x. These three are all representing the same exact idea. This notation on top is the notation which we call the Leibniz notation. It's written as L-E-I-B-N-I-Z, Leibniz notation. This notation here is something called the Lagrange notation, and this notation here is something called the Newton notation. These three people you might know, you might not know Lagrange, you might not know Leibniz either, but you definitely know Newton. Newton was one of the founders of calculus. He had a baseline idea of what calculus was, and he used that to construct a system of which you could find the rate of change of a function using this method. Leibniz was another person around the same exact time who also developed calculus. In fact, his notation, the dy by dx notation, is the more popular notation. However, this notation of putting a dot above a symbol to indicate the rate of change of that symbol is still very popular in physics. So you can say this thing is popular in physics, this is popular, and this is also popular in regular mathematics. Within our syllabus, we use all three of these notations in various different positions. So I want to put this out there. There are different ways to represent the same exact thing. The dy by dx notation method, the f dash method or f prime method, and the putting the dot above the symbol method. Each of these means the exact same thing. This is representing the rate of change of the value of f of x relative to x. This is representing the rate of change of f of x relative to x, and this is also representing the rate of change of, in this case, it's y, because we don't generally put f of x with a dot above it. We instead say that f of x is equal to y, and then we put like a y dot. This is representing the rate of change of y relative to x. All three of these are representing the same exact thing. For our purposes, for most proofs, we are going to be using this notation. However, for specific values, we are generally going to be using this notation. And within physics, you will often see this notation. So moving on, let's now discuss how we can actually find this value, whatever this function is that gives us the rate of change of a graph at a particular point for certain common functions. So let's get on to that right now. So the first thing we are going to do is consider a linear function such as this. For this thing, we're going to take one point, let's say this point here, and consider how we can find the rate of change of this function. But we already know this function is m. Let's see if our new method also gives us the answer m. So we're going to be interested in this value here, and we're going to be interested in the rate of change at this value here. So what we found is that dy by dx is going to be equal to the limit as dx approaches 0 of f of x plus dx minus f of x divided by dx. So in this case, the function f of x is going to be mx plus c. So we can replace that and say here this is equal to the limit as dx approaches 0 of, instead of f of x plus dx, we're going to substitute m times x plus dx plus c. So here we have m times x plus dx plus c. That's the first function, minus the second function, f of x is simply mx plus c. So over here in this bracket we have mx plus c, and then divide by the quantity dx. Expanding out this bracket, what we have is the limit as dx approaches 0 of, here we have m times x and another m times dx, so we can expand that as m times x plus m times dx, and then plus c, and then minus here m times x, we have minus m times x, and then plus negative c, so minus c, all divided by dx. Now here you can see we can cancel out mx to mx, negative mx here, we can cancel out the plus c to the minus c here. So then we can see this is equal to the limit as dx approaches 0 of cancelling everything, this thing goes to this thing goes to this, we are left with just m times dx. So we have m times dx divided by dx over here. Since we have dx approaching 0, this means that dx is not actually equal to 0 yet. So we can cancel out these two. This is not 0 divided by 0 because each of these values dx are not equal to 0. Recall that principle in limits where since this quantity is not actually equal to 0 yet, we can cancel things out like this. So then this is equal to the limit as dx approaches 0 of the quantity m. Since m here is a constant, it can be taken out of the limit. If you don't remember that rule, recall, go to this video here and recall that. So this is equal to simply the value m. So it works, it is backwards compatible. The limit as dx approaches 0 of this function here is in fact going to be equal to m. So it works for this function. Let's now apply the same principle to different functions and see what kind of results we get for those kinds of functions. So the next function we're going to be considering is the function y equals x squared. Applying this to this function, we're interested in this point here. We're going to consider another point, that is dx distance away, and apply this rule. So then here what we get is that dy by dx is equal to the limit as dx approaches 0 of, in this case what we have is f of x plus dx, which is x plus dx whole thing squared. So we have x plus dx whole thing squared minus the initial function, which is going to be x squared, divided by dx right here. So expanding this second term here, x plus dx whole thing squared, we can see this is equal to the limit as dx approaches 0 of x squared plus 2x dx plus dx squared minus x squared divided by dx. You can see here there's a plus x squared here and a minus x squared here. We can cancel the two, leaving us with the limit as dx approaches 0 of 2x dx plus dx squared divided by dx. Now again, since dx is actually not equal to 0, it's only approaching 0, we can cancel these here and we can cancel one of these dx squareds, dx's here. Then what we're left with is the limit as dx approaches 0 of, over here cancelling this to this, we get just 2x, and then cancelling one of these to here, we can get plus dx. Now then, considering what we have here, 2x is actually a constant relative to dx, because while we change dx, nothing happens to whatever the value of 2x is. So we can actually take that out. The limit of a constant is just that constant. So here we have 2x plus the limit of dx approaching 0 of dx. Well, as dx approaches 0, dx is going to approach 0. So this value here is going to be 0. So we have 2x plus 0. Removing that plus 0, we just have 2x. So therefore, dy by dx in this case is equal to 2x. What does this mean? This means that at any point x over here, the gradient of the tangent line here is going to be 2x. So let's say we have the point over here. Let's say this point is the point 2, 2 squared, so 2, 4. At this point, if we want the instantaneous rate of change of this curve here, that rate of change is going to be at x equals 2, the value of dy by dx, which is going to be 2 times, instead of x we need to substitute 2 into here, which is then going to be 2 times 2, which is going to be 4. So therefore, if you were to draw the tangent line to y equals x squared at this point here, what you would get is a gradient of 4 on this line here. If instead we do this point here, let's say this point is 5, 5 squared, so 5, 25 over here, and we draw the gradient at this point, as in we draw the tangent line to that curve, then what we are interested in is at x equals 5, the value of dy by dx, which is going to be equal to 2 times, instead of x we substitute 5 into here, so it's going to be 2 times 5, which is going to be 10. So if you were to draw y equals x squared and draw the tangent line to this curve at x equals 5, you would find that the tangent line has a gradient of 10. This is what we mean when we talk about the gradient and the derivative. So here we can see a simple example of how we can use the derivative and the derivative value in general of x squared. The next thing we're going to consider is generally, more generally, the gradient of the function y equals x to the n where n is some integer. So we are going to consider y equals x to the n for n being some element of the positive integers. So let's go. Here what we need is to find the gradient, as the gradient is, as in the dy by dx is the limit as a certain quantity dx approaches 0 of f of x plus dx minus f of x divided by dx. So here f of x in this case is x to the power of n. So here what we have is the limit as dx approaches 0 of, over here instead of f of x plus dx we can substitute x plus dx to the power of n. So here what we have is x plus dx to the power of n, and then minus f of x over here is going to be x to the power of n, and then divide by dx. We can expand this x plus dx to the power of n using the binomial expansion. If you recall, a plus b to the power of n is equal to the sum as r goes from 0 all the way up to n of the function n choose r times a to the power of r times b to the power of n minus r. Using this expansion, we can write that x plus dx to the power of n is going to be equal to, I'm going to take this whole thing to the left here, I'm going to shift this to the left so that we have enough space. This is equal to the limit as dx approaches 0 of, over here replacing this with the sum formula, this is sum as some quantity r goes from 0 up to n of n choose r times, in this case x, we'll say x to the power of, actually we'll do it this way, we'll do x to the power of n minus r and dx to the power of r, and then that whole thing minus x to the power of n whole divided by dx. So this is the quantity we are interested in. Now let's choose the different values of r and expand this sum into a continuous sum series notation. So here let's take the limit as dx approaches 0 of, in this case r needs to go from 0 up to n. When r is equal to 0 we have n choose 0 here, so we have n choose 0 over here, x to the power of n minus r is going to be x to the power of n minus 0 or x to the power of n, and then dx to the power of r is going to be dx to the power of 0 or just 1. Multiplying by 1 does nothing, so we're going to leave this as is. Plus the next term is going to be when r equals 1. When r equals 1, what we have is n choose 1, x to the power of n minus r is going to be x to the power of n minus 1, and then dx to the power of r is going to be dx to the power of 1 or simply dx. Plus the next term after that is going to be what happens when r equals 2. So we have n choose 2, x to the power of n minus r is going to be n minus 2, and then dx to the power of r is going to be dx to the power of 2 or dx squared. Plus, and then this goes on for a bunch of terms, and the very last term is going to be n choose, and here the last term is going to be when r equals to n, so n choose n. X to the power of n minus n is going to be x to the power of 0, so just 1, which we are going to ignore. Next to gx to the power of r is going to be dx to the power of n, so we have dx to the power of n, and then at the very end we have a minus x to the power of n here, so minus x to the power of n. The whole thing then is to be divided by dx. So here n choose 0. The n choose r function is n factorial divided by r factorial times n minus r factorial. When r is 0, we have n choose 0, which is n factorial divided by 0 factorial times n minus 0 factorial, which is going to be n factorial divided by 0 factorial is 1 and n minus 0 is n, so we have n factorial here. Cutting these two, we simply have 1. So therefore n choose 0 is equal to 1. How about n choose 1? Well, n choose 1 would be n factorial divided by 1 factorial times n minus 1 factorial. Here what we have is n times n minus 1 times n minus 2 all the way down to 2 times 1. On the bottom what we have is 1 times 1 factorial is 1, and then we have n minus 1 times n minus 2 times ... all the way down to 2 times 1. Cancelling all of the terms from the top and bottom, we can see all of this stuff cancels, and all we are left with is simply n. So n choose 1 is equal to n. We can substitute these two values in. In fact, doing so, what we get is over here on top, this n choose 0 becomes 1 and this n choose 1 becomes n. So substituting those two, this is equal to the limit as dx approaches 0 of 1 times x to the n is just x to the n plus, and the next term n choose 1 is going to be n, so we have n x to the n minus 1 times dx, and then plus, I'm going to leave the rest of them as is, as n choose 2 x to the n minus 2 dx squared plus dot 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 all the way down to n choose n dx to the power of n, and then minus x to the power of n, all divided by dx. Here you can see this x to the power of n and this x to the power of n can cancel, leaving only the rest of the terms on the top. And then you can see every single term here has some dx. This has dx to the power of 1, this has dx squared, the next term would have dx cubed all the way up to dx to the power of n. If we divide all of this by this bottom value dx, and again we can do this because even though dx is approaching 0, dx is not equal to 0. If we do this, we can see that this limit is equal to the limit as dx approaches 0 of this thing. When we divide by dx is just n x to the power of n minus 1. The next term is going to be n choose 2 x to the power of n minus 2 times dx squared divided by dx is just going to be dx. The next term after that would be n choose 3 x to the power of n minus 3 dx cubed divided by dx is going to be dx squared plus dot 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 all the way down. The very last term is going to be n choose n times dx to the power of n divided by dx is going to be dx to the power of n minus 1. Now this is the limit that we are interested in. We can see here the very first term over here is simply a constant. This term here relative to dx, as we change dx, nothing is going to happen to this term n x to the n minus 1, because n x to the n minus 1 is independent of dx. So therefore the limit of a constant is that constant. We can take it out as n x to the n minus 1. How about the rest of the terms? Well, the next term after that is some constant multiplied by dx. When you multiply by dx, since dx is approaching 0, this whole term is going to approach 0. So therefore this is equal to 0, plus 0. Plus the next term after that has a dx in it. Since dx is approaching 0, the whole thing is going to approach 0. So this is also 0. Plus all the way down, every single one of these terms at least has one dx. So they are all going to approach 0. The very last term also has dx some constant. So this is also going to approach 0. So we have n x to the n minus 1 plus a bunch of zeros, which is simply n times x to the power of n minus 1. So therefore the derivative of, or the gradient of y equals x to the power of n is going to be n x to the power of n minus 1. Representing this as the derivative notation, the derivative of x to the power of n with respect to x is going to be equal to n x to the power of n minus 1. The utility of this is that now we can find the derivative of any polynomial function, because here all we have in a polynomial is some x to some power n. So here we have a bunch of those terms summed together, which means we can then take the derivative of that thing. To do that, however, we need two more identities about derivatives, which we are going to discuss now. The first identity is when we have two functions summed together. Let's say h of x is equal to f of x plus g of x. Therefore h of x is a sum of two other functions. We are going to show that the derivative of h of x dx is equal to the derivative of f of x dx plus the derivative of g of x dx. How are we going to do this? Well, quite simple, using the first principle definition and some rearrangement using the laws on limits. The limit as dx approaches 0 of h of x plus dx minus hx divided by dx is the derivative of hx. So on the left side what we have is dhx by dx is equal to this. So substituting what hx is and what gx is, so what hx is in terms of f of x and g of x, what we have is that this is the limit as dx approaches 0 of, since h of x is f of x plus g of x, then h of x plus dx is going to be f of x plus dx plus g of x plus dx. So what we have here is f of x plus dx plus g of x plus dx. This is what h of x plus dx is, minus, and then we have h of x. H of x is simply f of x plus g of x. So this is what we have here. And on the denominator, of course, we have a denominator of dx. So here we have a denominator of dx. Now distributing this minus sign into this thing here like this, and then rearranging a little bit, we can see this is equal to the limit as dx approaches 0 of f of x plus dx minus f of x plus g of x plus dx minus g of x, and then the whole thing is to be divided by dx, but I can split that into two fractions as the first thing divided by dx and the second thing divided by dx added together. And now finally we're going to use one more thing. We're going to use the law of limits, where the sum of the limits is the limit of the sum. So here we have a limit of a sum, which means it's equal to the sum of the limits. So here we have to take the limit of this thing, the limit of this thing, and sum them together. So this is equal to the limit of the first thing, limit as dx approaches 0 of f of x plus dx minus fx divided by dx, plus the second limit, which is the limit as dx approaches 0 of g of x plus dx minus gx divided by dx. The first thing here is exactly what we mean by d of f of x by dx. It is by definition, by the first principle definition, exactly what we mean by the derivative of f of x with respect to x. The second thing we have here is exactly what we mean by the definition of the derivative of g of x with respect to x. So derivative of g of x with respect to x. Therefore, we can see from the left hand side being equal to the right hand side, by conclusion, d of h of x divided by dx is then equal to the derivative of the first function f of x by dx plus the derivative of the second function gx by dx. So there we can see that if you have a sum of two functions and you take the derivative, it is same as taking the derivative of each individual function and then summing them together. There's one more law we're going to apply, and that is the constant multiplication. This one's quite simple. If we say that, let's say two functions, let's say p of x is k times q of x, meaning we have multiplying by some constant here. Given this, I want to show that the derivative of px by dx is equal to k times the derivative of qx by dx, i.e. the derivative of a constant times a function is equal to the constant times the derivative of the function. To do this, what we are simply going to do is to state the first principle notation for the derivative, stating that what we have here is on the left hand side, d of px by dx is the limit as dx approaches 0 of p of x plus dx minus p of x divided by dx. So this is going to be equal to the limit as dx approaches 0 of, substituting p of x plus dx as k times q of x plus dx, we get k of q times x plus dx minus, and here substituting px as k times q of x, we have k times q of x, and then that divided by dx. Here we can factor out this constant k and write that this is equal to the limit as dx approaches 0 of k times, and then this whole thing of q of x plus dx. What we're left here is qx all divided by dx. So then here you can see we have the limit of a constant times some other function, which is equal to the constant times the limit of that function. So the limit as dx approaches 0 of q of x plus dx minus qx all divided by dx. Now here we can see we have k times, and the first thing here is in fact the first principle definition of the derivative of qx with respect to x. So this is dqx by dx. Now equating the two sides here, we have the derivative of px dx is equal to k times the derivative of qx. Px is equal to k times qx, so therefore the derivative of k times qx with respect to x is equal to k times the derivative of qx with respect to x. This is the second identity we are going to require in order to find the derivative of any polynomial. In fact, I'll do one example just to make it clear, and we'll move on to some other derivatives that we need to discuss. So here we have an example polynomial function fx. Let's try and differentiate fx using these rules. So what we want is the derivative of fx dx. This is going to be the derivative of this whole function here, which is 3x cubed plus 2x squared minus x and plus 7. So as we found, the derivative of a compound function or a sum of functions is equal to the sum of each of their derivatives. So this is equal to the derivative of 3x cubed dx plus the derivative of the next term, which is 2x squared dx, plus the derivative of the next term, which is negative x dx, plus the derivative of the next term, which is the derivative of 7 dx. So this is what we want to find. Now here I'm going to do one last thing. I'm going to put this 7 as 7 times x to the power of 0, because that's what a constant term is. Now we have the derivative of a bunch of terms. Recall that the derivative of a constant times a function is equal to the constant times the derivative of the function. Here we can take this out and say this is equal to 3 times the derivative of x cubed dx, plus over here we can take this as 2 times the derivative of x squared dx. Over here the next one we can take as the derivative of negative 1, so we can put minus 1 here and say this is minus the derivative of x with respect to x, as in x is x to the 1 with respect to x, and the last one is the derivative of 7 x to the 0, which is 7 times the derivative of x to the 0, so we can write this as 7 times the derivative of x to the power of 0 dx. Each of these we can evaluate here. The first one we have x to the power of 3, which is 3 times x to the 2, so we have 3 x to the power of 3 minus 1, which is 2, plus the next one is 2 times the derivative of this thing. X to the 2 is going to be 2x to the x to the 2 minus 1, which is 2x to the 1, so we have to multiply by 2x to the power of 1, minus, and then here the derivative of x to the power of 1 is 1 times x to the power of 1 minus 1, which is 1 times x to the power of 0, which is 1. So here we have 1, plus, and then 7 times x to the power of 0's derivative. X to the power of 0 is 0 times x to the power of 0 minus 1. This thing doesn't matter because here there's a 0, which means the whole thing is just 0. So finally what we have is 3 times 3x squared, which is 9x squared, plus 2 times 2x to the 1, which is 4x, and then minus 1, and this thing becomes 0. So that's it. This right here is the derivative of fx with respect to x, or we could write it as a different format. You could write either d fx by dx, or we could write it as like f prime x or f dash x, like this. We could also write it as like a y prime if we define this function as being, instead of fx equals 3x squared, 3x cubed plus 2x squared minus x plus 7, we could have written something like, y equals and this whole thing. And then in that case we could put y and a dot over it to indicate the derivative of y. So now that we've done that, let's go to the derivatives of some other functions. The first function we're going to talk about is the sine of x. So let's consider the function y equals the sine of x. And using this, let's try to find dy by dx. So dy by dx is going to be the limit as dx approaches 0 of the function at x plus dx, which is sine of x plus dx, so sine of x plus dx, minus the function at x, so sine of x, all divided by dx. So now then, what we're going to do here in order to get this into a simplified format and get rid of the limit is to expand sine of x plus dx. We know that sine a plus b is equal to sine a cos b plus cos a sine b. Therefore, expanding this thing, we have the limit as dx approaches 0 of sine a cosine of b. So we have sine of x cosine of dx plus cos a sine b. So this is going to be plus cosine of x times the sine of dx minus the sine of x all divided by dx. Now here the next step we are going to do in order to simplify this further is to take this thing as one separate limit and take this part plus this part as another separate limit. In order to do that, we're going to rewrite this as the limit as dx approaches 0. We're going to take this factor to the front, so we have cosine of x times sine dx by dx plus, and then this part we're going to write separately as the sine of x times the cosine of dx minus the sine of x all over dx. So now what we're going to do is split this limit into two pieces. We're going to have the limit as dx approaches 0 of the first part, which is cosine of x times the sine of dx by dx, plus the second limit, which is going to be the limit as dx approaches 0, and over here I'm going to actually factor out this sine next to the front, so it's going to be sine x, sine of x, times the cosine of dx minus 1 divided by dx. So here we're going to have the cosine of dx minus 1 over dx here in brackets. Now then, we can take some of these constants out. Over here, relative to dx, cosine of x is constant, because no matter what dx is, cosine of x is going to be cosine of x. So we can take that out and say this is cosine of x multiplied by the limit as dx approaches 0 of sine dx by dx. And this is going to be plus. Again here, sine of x is a constant relative to dx, because no matter what dx is, sine x is going to be sine x. So we can take it out and say this is sine x multiplied by the limit as dx approaches 0 of the cosine of dx minus 1 by dx. Now here, the cosine of x is going to be multiplied by this limit, which we know is 1. As anything approaches 0, sine of that thing divided by that thing is going to be approaching 1. So this is going to be 1. So here this limit is going to be equal to 1. So we have cosine of x times 1 plus the sine of x times this limit here, which for now I'm going to leave as L. We'll solve L and substitute L back again. So currently what we have is the cosine of x plus the sine of x times L. Considering L, let's take it separately and let's consider L. Considering L. L is equal to the limit as dx approaches 0 of cosine of dx minus 1 by dx. In order to simplify this, what I'm going to do is multiply the top and bottom by cosine of dx plus 1. So cosine of dx plus 1 divided by cosine of dx plus 1. There is no problem doing this, because as dx approaches 0, cosine of dx is going to approach 1. So basically we have 1 plus 1 over here, which is 2, divided by 2. Multiplying by 2 divided by 2 is same as multiplying by 1, which is the same as doing nothing. So this changes nothing. But what it does do is change our perspective. When we have this, we can see on top cosine of dx minus 1 times cosine of dx plus 1. What is this equal to? Well, we have a minus b times a plus b, which is the difference of squares. So what we have here is the limit as dx approaches 0 of the first thing squared, which is cosine squared of dx, so cosine squared dx, minus the second squared thing squared, which is 1 squared, which is 1, divide by, and then here we have dx multiplied by cosine of dx plus 1. Over here, what is the cosine squared of dx minus 1? Well, if you recall from this video here, if you haven't seen it, go check it out. The cosine squared plus sine squared of any angle is equal to 1. So therefore, the cosine squared of an angle minus 1 is going to be the negative sine squared of that angle. So this is going to be the limit as dx approaches 0 of the negative sine squared of the angle dx by dx times the cosine of dx plus 1. Now then, I'm going to use the identity of the product of two functions in a limit and say I'm going to take one of these sin x's out, one of these dx's out, and write this as the limit as dx approaches 0 of sin dx by dx times the rest of the limit, which is the limit as dx approaches 0 of, and what we are left with here, when we take one of the sin x's out, we are left with negative sin x on top, so negative sin dx, divide by, when we take the dx out, we are left with this thing, which is the cosine of dx plus 1. So we have that on the bottom. Now then, the first limit here we know very well, we proved it in the last video about limits. This is equal to 1 multiplied by the second limit. The second limit here on bottom, what we have is the cosine of dx as dx approaches 0, which is the cosine of 0, which is 1 plus 1. So over here we have 2. On top we have the sine of dx as dx approaches 0, which is going to be the sine of 0, which is going to be 0. So over here this part is going to be equal to negative 0 over 2, which is going to be equal to 0. So this second limit is equal to 0. using that we can replace this second limit by 0 and say this is equal to 0. So then the final limit we have is 1 times 0, which is going to be 0. So therefore over here this limit is going to be equal to 0. So I'm going to erase all of this rough work. You can keep it down somewhere if you want, or write it down separately as a separate proof, but we know that that limit is equal to 0. So then substituting that into here, instead of L here we can substitute directly 0 now that we've proven it. So therefore this limit is 0. So we have that the derivative of sine x with respect to x is going to be equal to cosine of x times 1, which is going to be cosine of x, plus sine of x times 0, which is going to be 0. So therefore we finally have cosine of x. So what we have here is that the derivative of sine x with respect to x is going to be equal to the cosine of x, hence proven. So now let's do the same exact thing but with cosine. Let's take the derivative of cosine and see what that gets us. If we take the cosine, we have y equals cosine of x. Taking the derivative of this, we have dy by dx is equal to the limit as dx approaches 0 of the cosine at x plus dx, so cosine of x plus dx minus the cosine at x, so cos x, all divided by dx. So here again we're going to employ a similar strategy to the one we discussed above, where we are going to expand cosine of x plus dx and solve it like that. So here what we have is the limit as dx approaches 0, and here we have the cosine of x plus dx. Recall that cosine of a plus b was cos a cos b minus sin a sin b. Therefore the cosine of x plus dx would be the cosine of x times the cosine of dx minus the sine of x times the sine of dx. And then we have another minus cosine of x over here all over dx. Once again what we're going to do is group certain terms and extract them. So here we're going to have the limit as dx approaches 0. Here what we're going to group is this thing separately and this divided by dx separately. So what we're going to do is have negative sin dx by dx, you might already see where this part's going, and then plus, and here we have cosine of cos dx and another negative cosine x. Factoring out that cosine x, we have the cosine of x times the cosine of dx minus 1 all divided by dx. You might see where this is going as well. Again, we're going to break this limit into two limits. We're going to take this part and take it separately, take this part and take it separately. On the left side, what we're going to have is the limit as dx approaches 0 of negative sine x times sine dx by dx, and then plus again the limit as dx approaches 0 of this time cosine of x times the cosine of dx minus 1 over dx. So now here evaluating this left limit and the right limit, this is a constant relative to dx because no matter what dx is, negative sine x is going to be negative sine x. Taking that out of the limit, we have negative sine x times the limit of sine dx by dx as dx approaches 0, so that's just 1, plus over here the cosine of x is a constant relative to dx because no matter what dx is, cosine of x is cosine of x, so we can take that out as a factor, multiplied by, and the cosine of dx minus 1 divided by dx as dx approaches 0, you will recall, is equal to 0. So now then, cancelling out that 0 part here, what we have is negative sine x times 1, which is negative sine x, plus cosine x times 0, which is 0. So therefore our answer is negative sine x. Therefore what we have is that the derivative of cosine x with respect to x is equal to negative sine of x, hence proven. Now let's try this for another trigonometric function, tan of x. So here what I mean is, let's take y equals tan x and find its derivative. Again, you might be getting the pattern, we're going to do the same exact thing. We're going to find dy by dx using the first principles and say that this is equal to the limit as dx approaches 0 of tan at x plus dx, so tan x plus dx minus tan x all over dx. This time, however, we're going to do something different. We're going to write the tangent of a function as the sine of the function divided by the cosine of the function. If you don't remember that, go check this video in the top right here. So we're going to write this as the limit as dx approaches 0 of, and tan of x plus dx we're going to write as the sine of x plus dx divided by the cosine of x plus dx, and over here minus the tan of x we're going to write as the sine of x divided by the cosine of x, and then all of this needs to be then divided by dx. Now what we're going to do is turn this thing into one common denominator. So I'm going to take this cosine of x and cosine of x plus dx as a common denominator, and then what we're going to get is the limit as dx approaches 0 of, over here we're going to have taking the common denominator as cosine of x times cosine of dx, we have cosine of x times cosine of dx, x plus dx, my apologies, x plus dx. And then on top we have the sine of x plus dx times the cosine of x, so the sine of x plus dx cosine of x, and then minus sine of x times cosine of x plus dx, so minus the sine of x times the cosine of x plus dx, and then all of this needs to then be divided by dx. So in fact I'm actually going to take this dx into this denominator here and put it like this. We have dx times the cosine of dx times the cosine of x plus dx on the cosine of x times the cosine of x plus dx on the denominator. On the numerator we have sine of x plus dx cosine of x minus sine of x cosine of x plus dx. Now you might be seeing something here, you might be seeing a difference of angles here. Recall that the sine of a minus b was sine a cos b minus cos a sine b. Over here we can see that we have that pattern. We have sine of this thing cosine of x, and then cosine of that thing sine of x. So here we can turn this back into this form and say that this thing is going to be the sine of, here a is x plus dx and here b is x. Substituting that in, on the top what we have is the sine of x plus dx minus x. So here we have the limit as dx approaches 0 of, and up here we have the sine of x plus dx first angle minus the second angle which is x, all divided by, and then here we have dx times cosine of x times the cosine of x plus dx. Now here what we're going to do is simplify the top, and we'll see the top is the sine of x plus dx minus x, which is the sine of dx. So writing that down, we have the limit as dx approaches 0 of the sine of dx, then I'm going to strategically put this dx down here, times 1 divided by, and here we have the cosine of x times the cosine of x plus dx. So we have the cosine of x times the cosine of x plus dx. This thing was strategic because we know what this limit is. So now we have a product of two functions, turning that into product of two limits of the function. We have the limit as dx approaches 0 of sine of dx divided by dx times, and then the limit as dx approaches 0 of, over here, 1 divided by cosine of x times the cosine of x plus dx. Now here what we're going to do is evaluate the left side function. The left side limit is 1. We know it's 1 because we proved it earlier. And then the right side limit, what we have is the cosine of x is going to be as it is. So we have 1 divided by cosine of x. And then over here, the 1 divided by cosine of x plus dx, when dx approaches 0, this is going to be the cosine of x plus 0. So just the cosine of x. So here we actually have another 1 divided by cosine of x. So here the final answer is going to be 1 times 1 divided by cosine of x times 1 divided by cosine of x, which is 1 divided by cosine of x squared. We have a special name for this function. 1 divided by cosine of x is called the secant of x. Recall this video over here. So here what we have is the secant of x squared. So what we have is the secant squared of x. My apologies, not theta, x. So what this gives us is that as a final result, the derivative of the tangent of x with respect to x is equal to the secant squared of x, hence proven. Now you might think we're done here because we proved the 3 trigonometric functions derivatives, but we're actually not done because there's another 3 which are 1 over the first 3. And spoiler alert, their derivatives are not 1 over these answers that we found here. They're completely different. So let's go to them. The first thing we're going to consider is y equals, let's say, cotangent of x. I'll explain why we're doing cotangent. It's because it's quicker and nicer compared to the other two, which are 1 divided by sine and 1 divided by cosine, or cosecant and secant respectively. Cotangent or 1 divided by the tangent is simpler than these. So here, for this thing, what we need is the derivative of dy by dx, which is the limit as dx approaches 0 of the value of cotangent at x plus dx, so cotangent of x plus dx minus the cotangent of x divided by dx. So here what we're going to do is, once again, similar to how we did it with tangent, for cotangent we're going to write cotangent of x plus dx as cosine of x plus dx divided by sine of x plus dx, and cotangent of x as cosine of x divided by sine of x. So what we're going to write here is that this is equal to the limit as dx approaches 0 of cosine of x plus dx divided by the sine of x plus dx minus, and then over here we're going to write this thing as the cosine of x over the sine of x, and all of this needs to then be divided by dx. So now what we're going to do here is take this under common denominator and simplify. So when we do that, we have the limit as dx approaches 0 of, over here the common denominator is going to have to be sine of x times sine of dx. Taking that up here, we need to have the cosine of x plus dx times the sine of x, and then minus the cosine of x times the sine of x plus dx. So cosine of x times the sine of x plus dx, and then all of that is then going to be divided by the common denominator of the sine of x times the sine of x plus dx, and then there's another dx here. This dx I'm going to take as here into this common denominator here. So now we have this. Now what we're going to do is some algebraic simplification. So here trigonometrically we can see we have a similar pattern to what we had above. We have cosine of one value, sine of another value, and minus cosine of one value, sine of another value. So again, recall, sine of a minus b is equal to sine a cosine of b minus the cosine of a times the sine of b. We can see that pattern here. If a is x and b is x plus dx, we have our pattern. So then a is x, so this is x, and this is x plus dx. So what we have is the sine of x minus x plus dx. So if we write that down over here, what we have is the limit as dx approaches 0 of, and on top what we have is the sine of x minus x plus dx. This needs to then be divided by dx times the sine of x times the sine of x plus dx. Now then, simplifying these things, on top what we have is the limit as dx approaches 0. Oh Jesus, that's not even a dx anymore. Let me write that again. Dx approaches 0 of the sine of x minus x, and then minus dx, so the sine of negative dx. The sine of negative dx divided by dx times the sine of x times the sine of x plus dx. So here we're going to strategically remove this thing in the next step, and we're also going to write that the sine of negative anything is equal to negative the sine of that thing. So therefore the sine of negative dx is equal to negative sine of dx. So using that, we're going to write this as the limit as dx approaches 0 of the negative sine of dx, sine dx by dx, you can already see where this one's going, multiplied by 1 divided by sine x times the sine of x plus dx. Now then, taking this limit and breaking it into two, because here we have a product of two functions, I'm actually going to take this minus onto this side and then break it. So when we break that like that, we are going to have the limit as dx approaches 0 of sine dx by dx, which we know is going to be equal to 1, multiplied by the limit as dx approaches 0 of negative, remember because we take that negative from this value to this value, we have the negative here, negative 1 over sine x times the sine of x plus dx. Now here, the first limit, we know what it's equal to, we found it earlier, it is equal to 1, multiplied by the second limit is negative 1, and then sine x is a constant relative to dx, because no matter what dx is sine x, so we have negative 1 divided by sine x multiplied by, and then 1 divided by sine x plus dx, as dx approaches 0 is going to be 1 divided by sine of x plus 0, which is going to be 1 divided by sine x. So we have 1 divided by sine x. So now then, simplifying this is going to be equal to the negative 1 over sine x squared. Again, we have a special name for the 1 divided by sine x. It is called the cosecant of x. So therefore, this is cosec x. So we can write this is equal to negative cosec squared of x. Again, some of you might not know this. I discussed this in a previous video, but I'm going to say it again. In Sri Lanka and some other countries, we write cosecant as this. You probably might write cosecant as CSC. Writing cosecant of x like this and like this are meaning the exact same thing. Both of these are identical. It's just that some people write CSC, some people spell it out like cosec. As far as I can see, only very few people do cosec. Most people write cosec as CSC. So here we have this result here. If we write this as a conclusion, we found that the derivative of the cotangent of x with respect to x is equal to the negative cosecant, cosecant squared of x. This is very symmetrical with the other derivative we found, which is that the derivative of tan x is equal to secant squared of x. The derivative of tan x is equal to secant squared of x. The derivative of 1 divided by tan or cotangent is equal to negative cosecant squared of x. So there's a kind of symmetry here. So let's go now on to the other two, which are the derivative of the cosecant and the secant of x. So now let's do the derivative of the cosecant of x. So y equals cosec of x. So here what we're interested in once again is dy by dx, which is the limit as dx approaches 0 of the value of the cosecant at x plus dx, so cosecant of x plus dx, minus the value of the cosecant at x, all divided by dx. So what I'm going to do here is to write the cosecant as 1 divided by sine. Similarly, over here, the cosecant of x plus dx is going to be the 1 divided by the sine of x plus dx. The cosecant of x is going to be 1 divided by the sine of x. So writing that out, this is equal to the limit as dx approaches 0 of 1 divided by the sine of x plus dx, and then minus 1 divided by the sine of x, all over dx. Next, what I'm going to do is take the common denominator here. So what I want is a common denominator of sine x times sine of x plus dx. So doing that, we have the limit as dx approaches 0 of, and over here what we need is sine x times this thing. So here sine x, then negative 1 times sine of x plus dx. So we have negative 1 times the sine of x plus dx divided by the sine of x times the sine of x plus dx, but here there's another denominator of dx. So here if we take those all into 1, we have the denominator of dx times the sine of x times the sine of x plus dx. Now then, here we're going to strategically expand not both of these sine of x plus dx's but only one. We're going to expand the one on the numerator. Expanding the one on numerator, we have the limit as dx approaches 0 of the sine of x minus, and in brackets here we need to put all of this. The sine of x plus dx is the sine of x times the cosine of dx, and then plus the cosine of x times the sine of dx. So here we have this, and then whole thing again divided by dx times sine x times sine of x plus dx. So x plus dx. Now here I'm going to distribute this minus inside, and I'm going to strategically move these symbols around into something that we will find interesting. So I'm going to do this and write this as the limit as dx approaches 0 of, I'm going to group these two into one and then leave this one separate. So I'm going to do here sine of x minus this, actually here we have the sine of x, here we have negative sine of x times the cosine of dx. I'm going to factor out the sine of x here and write this directly as 1 minus the cosine of dx, and then here this extra part which is negative cosine of x times the sine of dx, I'm going to write separately as negative cosine of x times the sine of dx. And then this whole thing needs to be divided by dx times sine of x plus dx, which I'm going to break into two denominators, and this denominator I'm going to strategically write as here sine x here dx, and I'm going to have an additional 1 divided by the sine of x plus dx over here. And over here for this denominator we're going to write the sine x over here, we're going to put the dx over here, and we're going to have the sine of x plus dx over here. So then taking these two, we can see we have a one set and then minus another function. So we have one function minus another function. The limit of one function and the limit of another function sum added together is equal to the limit of each of the individual functions added together. So this is equal to the limit as dx approaches 0 of the first function. Over here we can see sine of x divided by sine of x is going to be 1 if sine of x is not equal to 0. So then we'll cut that out. Cutting that out, we have left 1 minus cosine of dx divided by dx and a 1 divided by sine of x plus dx. I'm going to take a minus 1 out of here and write this as minus the cosine of dx minus 1 over dx multiplied by 1 divided by the sine of x plus dx, and then minus the limit as dx approaches 0 of this second thing over here. The second thing over here we can see there's a cosine of x divided by sine of x, which is 1 divided by tangent of x or cotangent of x. So this is cot x. Here we have sine dx by dx, so I'm going to write that as sine of dx by dx. And this part over here I'm going to write as 1 divided by the sine of x plus dx. Now here we can see a bunch of familiar things. Over here on the left, evaluating the left side limit, we know that this thing is equal to 0. This thing we know from earlier is equal to 0. Over here on the right side we have 1 divided by sine of x plus dx. When dx equals 0, this is specifically going to be equal to x, because here we have x plus 0, which is going to be equal to x. So we have 1 divided by the sine of x. Provided that the sine of x is not equal to 0, this is going to be some constant value times 0 times a minus. So this is going to be minus 0 times 1 divided by the sine of x. And then over here minus the limit of this thing over here. Cotangent of x is a constant relative to dx, because no matter what dx is, cotangent of x is going to be constant. So this is just the cotangent of x times the rest of this. The sine of dx by dx as dx approaches 0 is going to be 1. So this is times 1. So over here we have times 1. And then 1 divided by sine of x plus dx as dx approaches 0. This is going to be the sine of x plus 0. So that's just going to be 1 divided by the sine of x. So we have 1 divided by the sine of x. Now then, writing all of these things and removing the unnecessary bits, we have 0 times something, which is going to be 0. So this is part 0. Here we have negative cotangent of x times over here. This is 1 divided by sine of x or cosecant of x. Taking that to the front, this is usually written as negative cosecant of x cotangent of x. So therefore we have our answer. What we have here is the derivative of cosecant of x. So we can see derivative of cosecant of x with respect to x is equal to negative itself. So negative negative cosecant of x times the cotangent of x. Hence proven. Now then, we've done one of them. We've done 1 divided by sine or cosecant of x. Let's now move on to 1 divided by cosine or secant of x. So we have y equals secant of x, and we are tasked to find its derivative. Again, what we're interested in is dy by dx, which is, as you know, already know the drill by now. The limit as dx approaches 0 of the value of this thing at one value, so the value of secant of x at x plus dx minus secant of x divided by dx. So now here, similar to what we did with the cosecant of x, we're going to write this as 1 divided by cosine and 1 divided by cosine. So this is going to be equal to the limit as dx approaches 0 of the secant of x plus dx is 1 divided by the cosine of x plus dx, so 1 divided by the cosine of x plus dx minus, here this is going to be the 1 divided by the cosine of x whole thing divided by dx. Again, we're going to do the same thing of taking common denominator, in which case we get the limit as dx approaches 0 of, here we have cosine of x on top, so we have cosine of x over here, and then minus 1 times cosine of x plus dx, so we have cosine of x plus dx over here, whole thing divided by, over here the common denominator is going to be cosine of x times cosine of x plus dx with another dx on the bottom. Taking those all into one denominator, we have dx times the cosine of x times the cosine of x plus dx. Once again, we are only going to strategically expand the top. We're going to expand this cosine of x plus dx into its cosine of x and cosine of dx and sine of x and sine of dx. Doing that, what we get is the limit as dx approaches 0 of the cosine of x minus, and in brackets here, the cosine of x plus dx is going to be equal to the cosine of x times the cosine of dx minus the sine of x times the sine of dx. And then that's going to then be divided by dx times the cosine of x times the cosine of x plus dx. Now then, we're going to take this negative sign, we're going to distribute it inside the middle, and then we're going to strategically group these terms in order to get nice limits. So here with the limit as dx approaches 0 of, and over here I'm going to take this cosine of x and this negative cosine of x, cosine of dx, and group it into one term. I'm going to factor out the cosine of x here, so we have cosine of x times here 1 minus the cosine of dx. So we have 1 minus the cosine of dx. I'm going to strategically take that thing, separate it from the other term, which is negative times negative sine x sine dx, which is going to be sine negative times negative is positive, sine of x times sine of dx. And then divide by the common denominator, which I'm going to split again strategically. The left side, I'm going to write this thing as the cosine of x over here. I'm going to write the dx over here, and then I'm going to write on the right side the cosine of x plus dx additionally here. So additionally, cosine of x plus dx. Over here for this thing, I'm going to write the cosine of x over here. I'm going to write the dx over here. I'm going to write the cosine of x plus dx on the side over here. So these are the two limits that we're going to have to sum together. Here we have the sum of the limit is the limit of the sum. Here we have the limit of a sum. So therefore we can break it into two limits as this. On the left we have the limit as dx approaches 0. Cosine of x cuts to cosine of x provided cosine of x is not equal to 0. And then cutting those two, what we're left with is this part and this. So here I'm going to once again strategically write this as negative cosine of dx minus 1 divided by dx, because this thing in here is what we know, and then times this thing, which is 1 divided by the cosine of x plus dx, and then plus the limit as dx approaches 0 of the second part. Sine of x divided by cosine of x is tangent of x, so here what we have is the tangent of x, multiplied by sine of x divided by dx, so sine of dx divided by dx, times this bit, which is 1 divided by the cosine of x plus dx. Now, evaluating these limits over here, we can see this is equal to, here there's a negative, so negative. This limit we found earlier is equal to 0, so this is equal to 0, multiplied by this thing. When dx approaches 0, x plus dx is going to approach x, so we have the cosine of x. So we have 1 divided by the cosine of x. Plus, the second limit, here tan x is a constant relative to dx, because no matter what dx is tan x, so we can take that out as tan x. Over here we know the sine of dx by dx as dx approaches 0 is going to be equal to 1, so times 1. And over here, as dx approaches 0, x plus dx is going to approach x. So what we have here is 1 divided by cosine of x. Here, erasing all the unnecessary terms, the first term is going to equal 0. So erasing that, what we're left is tan x and 1 times 1 divided by cosine of x. 1 divided by cosine of x is called secant of x. So what here we have is tan of x times secant of x, which I'm going to write as secant of x times the tangent of x. Therefore, what we have as a conclusion is that the derivative of the secant of x by dx is itself secant of x times tangent of x. Notice once again the similarity and the kind of symmetry between these two. For cosecant, we have negative itself times the cotangent of x. For secant of x, we have itself times the tangent of x. So we have cosecant gives negative cosecant times cotangent, and secant gives secant times tangent. It's kind of a symmetry is there between these two. So that's going to be it for this video, since this video is taking way too long. It took too long to record, and it took too long in general. You can see probably it's very dark right now. The sun is going down. So I'll have the second part of this video, and it might even stretch to a third part. We'll see. But for now, we're going to end it there. So in summary, we discussed what a derivative is. We discussed the first principle of derivative. First principle derivative is this: dy by dx, or let's say f of x instead, d of f of x by dx is the rate of change of this function f of x with respect to x, which is the limit as dx approaches 0 of f of x plus dx minus f of x by dx as, of course, dx approaches 0. We then discussed a certain set of derivatives, common derivatives. One common derivative is x to the power of n, which gets reduced to n x to the power of n minus 1. So the derivative of x to the power of n by dx gets reduced to n x to the power of n minus 1. We discussed how we can use this identity and two others in order to find the derivative of polynomials. We discussed this other identity. If you have a constant multiplied by a function and you take the derivative of that, this is equal to the constant multiplied by the derivative of the function, so dfx by dx. We then also discussed the sum of two functions. If you have the derivative of f of x plus g of x by dx, this is equal to the derivative of the first function f of x plus the derivative of the second function g of x. So g of x by dx. We then discussed the 6 trigonometric functions derivatives: the derivative of sine, cosine, tangent, cotangent, cosecant and secant. So here they are. The derivative of sine of x with respect to x was found to be the cosine of x. The derivative of the cosine of x with respect to x was found to be the negative sine of x. Similarly, if we take the tangent, the derivative of the tangent with respect to x was found to be the secant squared of x. The cotangent, if we take the derivative of the cotangent of x with respect to x, was found to be the negative cosecant squared of x. We saw a little symmetry in these two. Furthermore, the other two, the cosecant and secant, are as follows: the derivative of the cosecant, which again, we are the only people who seem to be writing like this, cosec. Most people write cosecant as csc. The derivative of cosecant of x with respect to x is equal to the negative cosecant of x times the cotangent of x. And finally, the derivative of the secant of x with respect to x is equal to the secant of x times the tangent of x. That's going to be all for this video. We have much more to discuss. However, we'll be discussing that in the next video. For now, thank you for watching and goodbye.